and very effective. This applies about MySQL in the cloud, about MySQL on self-managed services, about MySQL on a VM. If you are running self-managed MySQL, you probably have a lot of these options to do on yourself, which it's good for flexibility. It allows you to basically choose everything between the operating system version, the operating system type, database version, how you go with high availability, backups. But there is also a burden that you need to scale your team. You need to take care of everything, starting from hardware lifecycle, server maintenance, how you design your HA solution, and so on and so forth. So while there is flexibility, there is also overhead. And if you move from on-premises to the cloud, immediately there are some benefits that the cloud offers. So for example, if you are running on a VM, you don't have to worry about operating system installation and hardware lifecycle. That's done for you. If you go with database as a service, then all of this will be managed for you. So the patching, the database software lifecycle and installation, backups, high availability, scaling, all that is done for you. So your team actually needs to only focus on app optimization, and this is actually database optimization and database performance tuning. If you want to migrate from on-premises to the cloud, the first thing that you need to start thinking of is how to provision your database. And there are a lot of options in the cloud. So even though this is a managed database, you still need to decide and choose. Each cloud has different options, but mostly there will be even free tier, so you can test, see how the cloud works with your application. Then you decide whether this is just a dev or test instance or it's production. And this is where it comes. All this is managed for you. So you have multi-AZ deployment, so high availability by default. Then you run on-demand or reserved instance. If you choose reserved, there will be some cost saving. The storage auto-scales, or you have just to check a button and your storage auto-scales, so you don't need to worry about disk growth and adding new disks. There are parameter groups, especially important for MySQL, because this is basically my.cnf in MySQL. In the cloud, it's called parameter group. Different clouds have different naming, but parameter group is AWS. Google calls this flags. It's eventually the same thing for the global variables. And then you have primary instance or a secondary instance. How you would migrate the data between your on-premises and the cloud. There are multiple options. And there are options that come for free, which you should utilize, because it gives you a lot of benefits, as like observability, what's going on with your instance, backups, you don't have to worry about backups. Mostly there will be at least 7 days free tier, or up to 35 days with no extra cost. So you just need to enable this, and it works. High availability, very important if you are running in production. AWS does this in 2 different ways. So here on the left, this is AWS RDS multi-AZ, which is multiple availability zone instance. You get a primary instance, and then there is another instance that runs in the background. It copies all the transactions synchronously, so In case the primary instance fails, this takes over, and it's done transparently for your application. However, this instance is not available for any reads. It's just there as a backup. And by choosing this, you realize that there is a second instance, so this doubles the cost for your environment. AWS allows another approach for high availability, which is creating multi-AZ cluster. So instead of one secondary instance that is synchronously copied from the primary, there are two instances in the cluster, and both are available in the reader endpoint of the cluster. So you can query, and you don't lose your rights just by connecting to a single primary instance. In GCP, it works more or less the same, and this is the same in Azure if you're running on the Microsoft cloud. So there is a primary instance, there is a standby instance, and the standby instance is synced synchronously with the primary. So this is not available for your application, but it's just a standby. If you want a read replica, then you need to create a read replica on your own, so your application can query the read replica. And for pricing, as you go with on-demand, the prices are high. If you start committing to the cloud, then the prices start dropping, and there could be up to 60% discount if you commit to using the cloud for at least 3 years, but usually it's between 30 and 50% discount, and different clouds will have these different discounts. Parameter groups, important thing if you are moving to the cloud. This is your my.cnf, and it's very important how you choose the parameter groups. One takeaway from this is that when you create an instance, there will be a default parameter group which you cannot modify. So creating a custom parameter group, assigning it to an instance, then modifying the custom parameter group will allow you to have flexibility. Using the default, you cannot modify anything. So very important to segregate your primary instance, primary cluster with your secondaries, and create different custom parameter groups. Database migration, so from on-premises or MySQL on a VM, migrating to database as a service, there are different options. Every cloud has database migration service. You can use logical backups, or you can use different tools like MySQL Workbench allows you to migrate from Oracle and MS SQL to MySQL. Before going to the cloud, if you don't have a custom parameter group, this will fail because of this setting. Importing store procedures in the cloud, you need a custom parameter group that will have this feature enabled. And the cloud doesn't allow some of the super privileges, so you need to understand that some of the security features are disabled, and if your application is dependent on any of these, you need to work that in advance. One note is when you deploy your instance initially, before loading the data, it might be wise to disable the multi-AZ, because loading the data will be waiting the sync to go on 2 instances, which may take you a little while. And this is also recommended to start creating the instance, so you have at least 7 days backups and performance insights. Minor version upgrades is enabled by default, and this might cause you downtime if there is a new minor version and the automation will kick in, it will start the upgrade, and your application might experience downtime. So This shouldn't be enabled by default, so you don't have unexpected downtimes. And also there is an option to protect the instance from deletion, so nobody can actually go and delete the instance by mistake. This is just one line command, how you would migrate from on-premises or from different databases as a service. Let's say your target is AWS, RDS, your source is Cloud SQL. You have a jump host somewhere in between that has connection to Cloud SQL and AWS. And the only thing you need is install MySQL shell, which is a tool from the Oracle MySQL. And you connect to the endpoint that is the source. And you run copy instance and provide these parameters. So what this will do is it will connect to the source, take the copy, transfer to the target, and apply the data set. So it's just a single command. And you just need to check your users and fix if there is any grunt that might not be working between the source and the target, import the users, and you're done. So that is just the primary copy. If you want to continuously replicate the source and the target, which might be useful if you want to do a cutover with as little downtime as possible, usually you would go with change master command or change replication source. This is deprecated in MySQL 8.4. So usually it will go this way, but in the cloud this doesn't work. What does is actually they created separate functions. So there is a call RDS set external master or call RDS set external source GTID purge. So these functions will allow you to make replication between the source and the target. At the end, you are ready for the cutover. You call reset external master. So on this instance, you will reset the external master and point your applications to the new instance. So that is maybe zero downtime depending on how your application buffers your writes. And once you are in the cloud, then it's easy to do this. Just create a read replica and the cloud will take all the burden from you. There is automation behind that will copy the instance, make the replication source, and you have a read replica. This can also be done with infrastructure as code or using the cloud development kit. And if you want, for example, in AWS, it's popular to migrate to Aurora. Migrating to Aurora, it's very easy. You just create Aurora read replica out of your instance, which is RDS. And then, once you have the Aurora cluster, you just promote it and point your application to the Aurora cluster. So again, as little downtime as possible. Major version upgrades. One thing that we learned is it can fail, but you can come prepared. If you do a major version upgrade, then your current version must be up to the latest minor. So, for example, latest is 5.7.41. If you are 5.7.20 and you want to upgrade to 8, it will fail. So you need to be up to the close minor version of the current. Additionally, there are some instance types that don't work with the next major version. You need to do your research. What instance classes work with your next major version and deploy that instance class, or else the major version upgrade will fail. And also, if you have custom parameter groups, you need to take care of the custom parameter before you do the upgrade. This can be done with blue-green deployment in the cloud, where the blue deployment is your current. There is a new green deployment. Everything is done for you in the background. Your blue deployment is copying to the green. Once everything is copied, you just point your application to the green environment and you do a cutover. So also a good feature that you have in the cloud. This can be used for major version upgrades with a failback. So if you are using this, it works only one direction. So the green environment is copied, but if you want to fail back later, there is no automation on that. That needs to be built by you. And it can be done by just using logical replication in the other way. Percona Toolkit, also something you can use in the cloud. These toolkits work with MySQL on-premises, MySQL on a VM, and it will work with MySQL in the cloud. I have a few examples how this will look like, but pretty much the same as it would to any MySQL environment. Very rich performance insights. This comes in AWS with performance insights. If some of your instances doesn't support this, you still have the option to use PMM, also very rich with graphs and dashboards. This is Grafana-based dashboard. Some of the performance issues that typically arise in the cloud and you mostly will work at one point, it's not related to your configuration. So this is the last thing to check. Might be related with with low resources on your instance, but it's mostly related to your workload. So evaluating instances and troubleshooting for performance, this is where you start, like check your queries, your indexes. Do you have queries that don't utilize indexes? What is the complexity and what is your concurrency? Scaling, horizontal, vertical, you can scale up, you can scale horizontal. This is very easy in the cloud because it's just a few clicks, or you can even declare this in your code. But there are limits. So you can only scale vertically up to some point. After that, you cannot scale anymore. So you need to be thinking about horizontal scaling by sharding. So this is the way to go with horizontal scaling. Shard your instances horizontally. Don't use your data on a single instance. AWS has this feature auto-scaling for reads. Aurora can auto-scale your read capacity by providing some CPU utilization targets and average connections. For security, because you are in the cloud, you have some of the cloud security guarantees that is the responsibility for the cloud, and that makes you compliant by default. But there are additional responsibilities for your team, so you need to be looking at the operating system, your platform, your users, and your client data encryption. So that is still important, and it's for your teams. Prompt engineering, this is something that works with any database, and it will work with the cloud as well. So you can use prompts to generate code for your database and test your application. And still, there are some features that only exist in the cloud. That's where the automation is, and that's where the evolving comes. So this is only available in the MySQL HeatWave environment in the Oracle Cloud. Like they continuously develop new features like this hypergraph optimizer. You have vector store generative AI in the OCI HeatWave, autopilot indexing, and JavaScript store program support. I don't know how many of you are aware that there is a HeatWave product from Oracle, but it's a database as a service. So it's something that you can explore and test. And with that, we're done. Thank you.
Thank you very much. Are there any questions?
Yeah, you mentioned prompt engineering
Yeah.
for testing the database. What kind of testing is that?
So prompt engineering is basically, this example is showing you have some database in your production environment, and what this particular use case will do is you want to test something in your dev environment. So this prompt will just give you 10,000 random records in your test environment with the same table structure. So you don't need to worry about masking the data and maybe security compliance. You just do that on your test dev environment, and it will do the job in 1 minute for you. So it's very easy.
Any more questions?
I assume the minor upgrades with like AWS and that kind of thing, they all fail over to the other node while they're actually doing the upgrade at the same time. Is that how it works?
Sorry, didn't.
The minor upgrades.
The minor upgrades.
The auto minor upgrades. Do they fail over to the secondary?
The minor upgrades, no. So the minor upgrades are applied on the instance itself, but you can choose to promote a new instance if you decide to do so.
Okay, but if you do an auto minor upgrade, does that mean you're going to get a downtime at a random time?
For managed database service, yes. So it needs to restart. Yeah, that's where you actually need to plan. You need to plan.
Okay. Next.
Any more questions?
Oh, sorry.
Okay, thank you very much.
Thank you.
So we can invite.
Yes, and click. Is clicker working?
Clicker will work. This wasn't focused.
We got it.
Now, click on open Google Slides. It won't work otherwise. And then slideshow.
Which is where?
Slideshow.
Left. Yes. You also need glasses. So try this.
Is it working? Is it working?
Try.
That's
Okay.
great. I will put it.
Okay, for our next speaker, we will be having Alexander Zavaikin, who is a PhD in technical science and a group leader at YDB. He will be giving a presentation on YDB, how to implement streaming RAG in a distributed database. Please welcome Alexander Zavaikin.
Hello. My name is Alexander Zavaikin. I work with an exciting project named YDB, and I have the privilege to share with you my passion AI in big databases. And one of the interesting tasks is how to implement streaming retrieval augmented generation in a distributed database. Let me move towards streaming RAG. But at first, I would like to say a few words about RAG itself. It makes no sense for enterprises to develop their own AI models. Simply put, it's too complex and too costly. Not only does it require millions of dollars, but it also requires compute infrastructure. That is why they rely on models who have already done the most expensive training on vast amount of raw data. And here, RAG is needed to use domain-specific enterprise data. I want to give you an example of RAG. Can you imagine a user wants to know what is the cinema poster in Paris tomorrow? But he asks simply, what can I see in Paris? And LLM doesn't know anything about Paris, about cinema posters, and so forth, because it has been trained only on historical data. Using the chat history, new facts could be added to the prompt, cinema poster, and tomorrow. The prompt is passed to the embedding model, and the embedding is passed to the vector database. The vector database returns all the facts about cinema posters in Paris tomorrow, and the user query is augmented by these facts. Inference with RAG is most valuable when used in real time. For example, you can see that lag between versions of ChatGPT could be as great as 1 year. AI without up-to-date data is frustrating, and its value is limited. Let me speak about typical use cases of streaming RAG. In the finance sectors, it offers immediate, data-driven approach into stock market opportunities. In healthcare, critical real-time data could redefine patient monitoring and diagnostics. News organizations access real-time insights about news events enhanced with the latest updates. Let me move towards YDB. YDB is a distributed database. It combines high availability and scalability with strong consistency and ACID transactions, dealing with petabytes of data on thousands of servers. And we are available open source. You can download us, try us, both in Docker installations and on-premise installation, on serverless clouds, and so forth. YDB is a platform that offers a variety of ready-made large blocks. They complement each other and facilitate development. Vector search and topics are typical blocks that are built on top existing ready-made complex functionality. Having built-in vector search engine and topics has many advantages. It doesn't need complex infrastructure. Scaling and making production ready are Herculean tasks. For example, sharding and replication on thousands of servers requires enormous expertise. Here, I would like to introduce the architecture of streaming RAG in YDB. On the left, there are several data sources, both row and column-oriented. Using change data capture, the flow of data is delivered to the stream processing. The text payload is extracted and passed to an external encoder, which is a typical neural net transformer. Vector embeddings are generated and returned back to augment original data. Finally, embeddings are stored in the vector index. Now I would like to pass the microphone to my colleague Elena, who will tell you about streaming itself.
Hello to everyone. My name is Elena Kalinina. I am a technical project manager in YDB, and I am responsible for YDB topics and implementation of persistent queues within YDB. Sorry, the slide is not full, so I will tell you by words. As Alexander said earlier, YDB is a platform which provide you possibilities to work with OLTP, OLAP, and streaming workloads. And YDB topics is an implementation of persistent queues within YDB. And maybe you are familiar with Kafka. YDB topics have the same model as Kafka, but we suggest much more than classical Kafka. So the data model is the same. Every topic is a log of messages. Topic is divided into the partitions for scalability, and several writers can write into the one topic at the same moment, and several readers can read from one topic at the same moment. YDB topics provide high throughput. We have inner installations which in several availability zones which have overall throughput of hundreds gigabytes per second. And YDB provides all this throughput. Also, YDB topics provide appropriate message delivering guarantees, at least once, or even exactly once, if you need it. You can work with YDB topics through our YDB native SDK. In this case, all our specific features are possible. And you can use Kafka API, and Kafka compatibility allows you to work with standard Kafka instruments and integrate with such solutions as Logstash, FluentBit, Spark, and so on. Okay, let's go deeper. What can we do with topics for RAG? As Alexander said earlier, first is change data capture. In YDB, you can create topic, change feed for capture any changes from some table. And YDB provide exactly once delivery for every change. Change records are sharded across topic partitions by the primary key, and the order of changes also provides by YDB. And high throughput, of course. You can see a simple example on this slide. We created a change feed for the table 1, and there were two changes in this table. First change was an update of 2 rows, and change records were delivered into the partition 1, partition 0 and partition 1, corresponding to keys of records and primary keys of records. And second, change was deleting row from a table 1, and corresponding change record was delivered into the partition 1. And you then can use this change feed for the further reading and further processing of this data inside this YDB database or outside if you need. Also, we provide specific tool. We have a specific tool to transfer data from topic to table with a simple YQL statement. YQL is an SQL dialect which allows you to perform a rich set of operations with topics and tables. And one of these operations is creating transfer. As you can see, the code is very simple. All complexity is under the Lambda expression, and you can do any complex data transformation in it if you want and if you need with your business logic. And this is our proud. We developed really revolutionary thing for the data world. In YDB, you can work with tables in topics within a single transaction. And YDB provides all ACID guarantees for such operations. So you can do any transformations with topics involving many tables and topics from one database within a single transactions, and YDB provides all consistency and all ACID properties of such operations. What does it mean for RAG? Let's see a simple example. Let's imagine that we have a source topic on the left with simple events. For example, user clicks from some search engine. Also, we have a table with rich user profiles, and we want to enrich user clicks with some data from user profiles. In YDB, you can, in one transaction, read a simple event from source topic, then enrich it, do some transformation with data, and enrich this event with data from user profiles, and then in the same transaction, write this event into the receiver topic with enriched event. In YDB, this is a single transaction which can be completed as a whole, or it can be aborted in case of some conflicts. And all complexity of transaction processing is on YDB side. You, as a developer, should think only about your business logic. If you want to implement a similar logic in case of having tables and topics in different systems, for example, you have topics in Kafka and tables in Postgres or some other database system, you should not only implement simple business logic or relatively simple business logic, but you should think about providing all transactional guarantees. What should we do in case of lost connection to system with topic? What can we do in case of rollback transaction in database system? And how we can provide consistency of our data and atomicity of transactions, and so on. And YDB is do all base job for you. It's not really simple job. And I want to emphasize that this is a really distributed transaction, that which data can be stored on different nodes or even in different availability zones. So, to summarize about transactions with topics and tables. We add ACID guarantees to topic table operations. It simplifies user code, and it has minimal impact on latency. Topic table transactions is a very complicated thing, and my time slot here is really short, so if you have some more questions, you can find me and Alexander. We have a booth just opposite this hall, and we are glad to answer any questions. And for the topics, last but not the least thing which is very useful for high throughput is topics auto-partitioning. As I said, every topic is divided into the partitions for high for scalability. Every partition has a maximum throughput depending on installation. And if you are not sure about maximum throughput of the topic on its creation, you can, in YDB, you can create topic with auto-partitioning, which means that partitions count will be increased automatically on increasing throughput. It will be done transparently from the user, and YDB, as always, provides all guarantees, exactly once for writing for all writers and reading order for all readers of this topic. So, what YDB topics can suggest for RAG? Actually, YDB topics provide all necessary thing to create a whole system of many sources and receivers which can operate with high throughput. You can deliver table changes with change feeds, transfer data from topic to table with our transfer tool. You can do any topic table data transformation within classic ACID transactions. And we have topics auto-partitioning for smooth scalability. Of course, we provide our base properties, high throughput, reliable, and also we are Kafka compatible. So, I told you which features and what we have for stream processing in this architecture. And let me hand over back to Alexander, and he will tell you how we can create a vector index, which is necessary part of streaming solution.
Thank you, Elena, for bringing to life the process of streaming. Let us return to the vector index. I would like to start from quite strict requirements. Many of those are originated from the very nature of a distributed database. Our goal is to store billions of vectors. That is why index should scale in a linear way. Another quite a strict requirement that index should be both synchronous and consistent. Many algorithms have already been invented, but they do not suit our very strict requirements. YDB is a distributed system. That is why automatic scaling is important. On the other hand, YDB has strong consistency. It means that index should be also consistent. Here are our SQL commands for creating vector index on the left. You can create vector index with a special type. You can use some column names, some vector parameters like vector type, vector dimension, and so forth. And on the right, there is a SQL command for selecting to find top key vectors nearest to the target. And target is the vector embedding which is passed by the user. Let me switch to internals of our vector index. Here are, on the left, vector space split into several vector clusters. Each vector cluster has its centroid. And all the centroids form classical information retrieval index, like an inverted list. You can see in the middle the buckets of centroids in the middle, and on the right you can see posting lists of vectors. And by the way, posting lists are stored in the usual data tables, and we know how to deal with such tables. But this approach has one drawback. If the data set is huge, the number of clusters is huge also. The solution is to use some space pruning algorithms. Maybe some of you are familiar with so-called R-tree. There are small red clusters. They form bigger blue clusters. So forth, black clusters are formed. Finally, we see a tree of clusters. And this very structure can easily cope with a huge number of clusters. Let me return to the internals of our vector index. We form the same hierarchical structure of clusters like folders on your file system. Purple clusters form blue clusters, which becoming bigger and bigger. We managed to store this tree structure in several usual data tables. And do not forget, we have long-term experience how to scale such tables. That is why we are capable of indexing billions of vectors. Another quite an outstanding feature I would like to stress is the filterable vector index. The original select query is added with where predicate, and internally it's quite difficult to process. If you filter before vector index, you can't use index because it optimizes only whole queries. And you have to use full scan after filtration. If you filter after vector index, the number of vectors will be reduced, and that may be not enough. And you have to repeat query, increasing the key limit. It obviously affects latency. The solution is to implement filtration capabilities inside index. And we have created well-known secondary index on the top. And every key on 3 leaves has its own vector index, which is used for vector search. Vector index 1, 2, 3, 4, n. And this idea is brilliant by its simplicity, but some believes it too wasteful to have too many vector indexes. For our implementation, it doesn't matter. Recently, I have shown that our index is stored in a constant number of internal data tables. That is why we are capable of indexing an unlimited number of vectors. Finally, I want to show you how to cope with index update. A new vector is added, it's located in some cluster, and we put the vector simply to the end of posting lists of that centroid. It's just a constant number of steps. Of course, we have a tree of clusters, and this change should be pushed up through the levels, but the height of tree is also constant. If I had more time, I would be happy to tell you more about other features of our exceptional database. But because our time is almost over, let me invite you to our booth, just opposite the hall, to discuss the following subjects after my presentation: how to try YDB, its excellent scalability, the secret of its robustness, last but not least, what clients' utilities and languages are supported. Let me conclude by summarizing the main parts. YDB is a distributed database that combines high availability and scalability with strong consistency and asset transactions. Recently, we are moving towards AI. Thank you for your attention. Feel free to come to our booth.
Thank you very much. And also, I want to apologize for my announcement earlier. I did not scroll down to see Elena Kalinina. She is the technical project manager at YDB. I apologize. Any questions for Alexander and Elena? Sorry, Elena? Yes, microphone here.
I see that you made a Kafka compatibility layer. What was the reason for that, and what would be the use case where I would prefer YDB over Kafka or Kafka over YDB?
As you know, Kafka is the world's most popular decision for streaming, and we started, I think, maybe 2 years ago, and we have inner Kafka installation, and it wasn't enough for us. That's why we decided to have our own streaming decision. And YDB topics can suggest you much more than classic Kafka. For example, topic tables, transactions, and auto-partitioning. That's why you can prefer, in some cases, to use YDB topics. High throughput, of course, too. Thank you, Alexander, but Kafka, it's not quite bad from this point of view. But if you have some code which was written for Kafka, it's maybe it can be useful to use your code with YDB topics in transparent way. So you can work with YDB topics as Kafka topics. That's why we developed this layer of Kafka compatibility.
Thank you. Any more questions? In the back.
Yeah, I'm a little bit curious about like the database architecture, because so you say it's a distributed database, but then there was like this one slide where you were presenting inputs like you have your analytical tables and your OLAP table or TP tables, yeah, that one. So this is like separated in YDB, or are these data sources not even part of YDB, or like, yeah?
YDB is a distributed database which give you possibility to work with OLTP workloads and OLAP workloads in one database. So we have classical row tables for OLTP workloads within one database, and you can, in this database, create the same database, you can create topics for streaming workloads and then interact between them.
Yes. I would like to add that this yellow rectangle YDB, it means that this is the whole cluster. And can you imagine thousands of nodes? Thousands of nodes, partially for OLAP tables, partially for OLTP tables, partially for streaming processing. But this is a single cluster. And within single cluster, you can use transactions. That's great. You can use vector indexes and so forth.
Not only one cluster, it can be distributed between several availability zones. And distributed transactions between several availability zones are provided with YDP. And all these inner instruments too.
Good, thanks.
Thank you. Any more questions? Is there a question over there?
Elena, really quick one on your auto scaling. You said, and it implied that all the auto scaling up. Does it auto scale down as well, or no one ever auto scales down?
You are speaking about after partitioning. We have after partitioning both for ordinary tables and also for topics, and that's a great distinguishable feature for our topics, for example, because other topics can't do it. And our table is after partitioned also. For example, you can create small table, ingest there a lot of data, and this table increases through many servers.
Okay.
So does topics.
So one shard from table on one node, another shard on another node, it's sharded by the primary key. And the same for topics. One partition on one node, one partition on another node, maybe in several availability zones. And if topic has a feature, if topic was created with auto partitioning, YDB on increasing throughput can divide some partition into the two partitions, and YDB provides transparency of these operations for all clients, but you have more and more possibilities to write into this topic and to increase your throughput for this topic.
Okay, that makes sense. Thank you.
Thank you.
Thank you. Any more questions? All right, well, thank you very much.
Thank you.
Thank you.
Feel free to have more questions on our booth. Thank you.
We will be having a short break, and we'll be back at 10:45 in about 15 minutes.
Hi, a very good morning to all of you. I'm Gary, I do the video, but I was given the honor to introduce this fine gentleman who happens to be my very good friend, Richard. He's gonna introduce you some things about monitoring and observability. So Richard, please come up. He's the Director of Community at Grafana Labs, so give him a warm welcome.
Thank you. Should this monitor be working? Ah, okay, good. Then I'm just going to stand and pretend I know what's on my slides. So, yeah, I need to hurry a little. Those should be skipped. That's not in the PDF. I'm sorry. So, when you think about observability today, something which often happens is you have a lot of disparate systems, and you need to rethink while you are in an outage or while you're trying to debug a problem. Like if something is maybe orange is good in the one system and green is good in the other system, or the graph is subtly different, you have a different scale, different name. It takes a lot of mental overhead and effort to really understand what is happening. And in particular at 3 in the morning, that's a bad thing. By extension, this also makes it harder for you to externalize this into computer code. So not only does it make this harder for you as a human to move and understand what is happening, but also it makes it a lot harder to put everything into code and basically put yourself out of your today job and do a more impactful job tomorrow. Also, one editor's note, apparently the export of the PDF includes skipped slides, so I will sometimes apparently have to click more often. So, let's rethink how these disparate systems can be done, and also let's really walk back a lot and come back to the basics of how humans have dealt with data over thousands and thousands of years. Ever since we have had written records, humans always went through the same optimization chain. And by extension, I'm arguing that we should do the same in computer science. So if you look at this is a power meter by Janitza. They are the market leader, the European market leader for power measurement. And what you can see is, on the one hand, a graph, basically how good the power is as it comes in. Do you have any desynchronizations on your sine wave and everything? And also you have logs. The pattern, which you will always observe in any established industry, is that the vast majority of data is going through numbers, because numbers are the most efficient. And anything which is really, really like a short time or really important, let's say a power outage, or let's say a security incident, or something which is money related or something, you put this as distinct events, because those are more important, and there you can pay the extra overhead of storing this. I'm going to talk more about this once I'm done with my history lesson. This is the Stahlschlüssel. This contains every type of steel which is being produced on Earth. This book has been in publication for over 100 years, is re-released every few years. Every single steel manufacturer on Earth, with all the properties of all the steel which they're offering, including manufacturing quantities and everything, is in this one book. All the properties are just numbers. The chemical composition, the tensile strengths, the everything, it's all numbers. Without steel, I mean, the world wouldn't work, and everything about steel is in the numbers. There's a logbook, the classic example for logs and where the name is coming from, where when they were on the high seas with their ships, they threw the log overboard. They counted the knots on the rope which they tied to that piece of wood. That's also where the speed in knots is coming from. And this is how they determined how they were on the high seas. And there's something very easy. If you're sailing on the high seas and you don't know where you are, you die. It's very easy. So this book was absolutely sacrosanct. The absolute most important information about this book was put in there. And over time, obviously, they also started putting in like cargo, who got paid, all of the essence of the book as to the outside interface to the world. This is the oldest letter we know of, like 4,000 year old. It's a complaint letter about someone selling the wrong grade of copper, the seller being not nice to the servant of the buyer, and also the seller making provisional payment. This is basically the full story of what happened, but it was an important transaction. And this is the oldest writing which we know of that is most likely tabulating who owned what slaves. My point here is this. Humanity always goes through the same cycle. Something is worth doing, I write down the whole story. As this keeps being worthwhile, as I keep doing this, this becomes too expensive. So I start to extract the key events. This makes it much cheaper and much easier to deal with all my data. As I keep doing this, as this keeps being worthwhile for whatever I'm doing, this becomes too expensive. So at this step, humans have done the same thing over and over again. They have put information in the best and the most dense format which we as a species know of, and that is numbers. Numbers are great. You can do math on them, you can store them really efficiently and cheaply, you can do large-scale statistical analysis on them. They are absolutely great. And any established industry, again, is fully numbers first. Like if you get paid, you get a number into a number. That's the money into your account. Then you consume your water, electricity, and internet, whatever. You get numbers from them. That's the consumption. You get another number. That's the price per consumption. You get another number. That's what you have to pay. And you send that number to a number, and that's their account. It's all numbers. And yes, by extension, because IT tends to be log first, my argument is that a lot of IT is not yet super mature and optimized and could be doing better. I should have been on this slide, but I don't have a monitor. Anyway, let's look at a few buzzwords and other things. So observability is a super cool buzzword. And no one is doing monitoring anymore. Everyone is doing observability. Of course, this makes your boss more happy and it gets you more money maybe. And also you sell better. Just call the old thing by the new name. And that is how you do it. But the thing is, buzzwords usually have a kernel of truth, a reason why they have been successful. Who here has heard of the term cargo culting? Oh, surprisingly many. So for those who don't know, this comes from the Second World War, where during the war effort in the Pacific Islands, a lot of soldiers came to remote islands, some of which had never had contact with humans before, or at least only very controlled contact with humans. And those weird people, like the indigenous people, observed those weird other people coming and clearing out forests and building little fires and turrets and walking around. And they did all this, and all of a sudden, the gods started sending gifts from heaven. Those were planes and ships dropping cargo for the war effort. But the indigenous people didn't understand this because they didn't have the context of what was happening. So they just observed the behavior of someone is clearing the forest and they're marching along. And also all of a sudden, huge amounts of cargo come to this island and everyone is rich all of a sudden because they have all this stuff. They did not understand what was happening in between. And this power is so strong that even through these days, where those people absolutely 100% understand what was happening, they still have proto-religions in the region, which is where the term cargo cult is coming from, where they still do small marches, build control towers and landing fires and everything as part of their local traditions and religion. This is how deeply this desire to copy and to emulate perceived success is ingrained in humans. So it's not a bad thing for everyone to just try and do the thing which is so successful. But also a lot of salespeople will just tell you, oh no, it's complicated, and then sell you more stuff. So monitoring, my own, like I use them interchangeably, absolutely. There are, let's skip this. Observability at the core is about enabling people to understand stuff, to understand systems, and by extension, again, to make computer systems understand stuff. There are some functional tests for the term observability. Those are the ones which have initially made the term popular within computer science. If you cannot ask new questions on the fly, it is not observability. If you can only determine that something is broken and not why something is broken, which is basically the same thing as the other definition, it is not observability. So those are functional definitions. They are not super precise and useful, and maybe sometimes that's in favor of the salespeople. I've also seen in seriousness, have seen terms suggested as observability 2.0 and 3.0 and 4.0. And on the internet, everything goes up to 11. So let's just call it observability 11 and be done with it. No, my point here is you can see how this is still the buzzword cycle. Like if I have to try and redefine a term which has been a few years old, probably I'm trying to just keep the hype cycle alive. But is it only a few years old? So the initial first scientific reference which I could find is from 1809 from Carl Friedrich Gauss. That basically what you have to do is you have to make more observations about the absolute of the state of the world, like a little bit more than you absolutely need, because you might miss some. to be able to make determinations about the state of the real world. And same as we currently with cloud native and all of this explosion of services have vastly more data, in the 60s or in the 50s, something which happened is industries and factories became too large and they couldn't have this one person who knew everything, and they had to actually do science on how to make this comprehensible if more than one human has to share the understanding of what is making the money and the products. So they invented control theory and poured a lot of money into universities to study control theory. And this is where this definition is coming from 1960. Observability is a measure of how well internal states of a system can be inferred from knowledge of its external outputs. That is the scientific definition of observability. You do not need anything else ever again, because this allows you to reason about, is the system actually able to tell me about itself, or do I need to add more signal? Or maybe can I take away signals because I'm just paying too much and dial in that I have just a little bit more than I absolutely need, and that's the perfect happy place for observability and the amount of data which I'm generating. We also have to talk about complexity. I personally like to discern two different types of complexity, fake complexity and real system inherent complexity. Fake complexity, get rid of it. You do not need that new JavaScript library. You really don't. Like, you have to collect them all, but not here. So you don't always need extra complexity. Important point, if you are in a regulated business, like finance or whatever, those laws and regulations are very much fake and invented, but they are very real for you. So yes, they do apply and you have to take them into account. Real system inherent complexity, you cannot get rid of, because this is part of why you even have the thing which you are responsible for. Otherwise, it wouldn't exist. So you can move it. It doesn't really matter if it's on a mainframe in a monolith or if it's in a fully cloud native microservice, blah, 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 horizontal, scalable, whatever. Doesn't matter. The complexity itself lives somewhere. You must compartmentalize it, else you cannot understand the total amount of complexity. You must put in layers where you can understand. It should really be distilled meaningfully so you can actually understand it. And again, you can't reduce it. So what's a service? Services are compartments of complexity. And they usually have different owners and teams and everything. And the interfaces are traditionally called APIs. I prefer the term contract, because a contract is something like API, I just change it, it's the other person's problem. But the contract, I have to sit down, I have to talk, I have to agree, I have to write it down, everyone puts their name to it. This is the agreement, this is the contract. Oh, okay, we're going to speed up. The other thing which we have here is the term layer. The internet is basically a just layered on top of each other. It doesn't matter if you have fiber or if you have Wi-Fi, it just works. There's plenty of other examples. Cloud native, it does again not really matter where your complexity lives. The main thing about cloud native is you can break stuff up into horizontal units and you can scale them horizontally. It's easier to scale horizontally than to scale vertically. But the other unspoken part about cloud native very often is as I have my hard API contracts, I do not have to have my people talk to each other as much. The teams don't have to interact as much, which means they can spend more time engineering and actually doing stuff which is worthwhile instead of just having endless meetings by making those compartments of complexity smaller. I just allow them to work more independently as long as they have good API contracts. But there's a problem. I'm deliberately breaking up previously well-contained units of complexity. Previously, I had my one binary running on my Linux machine, and I had top and all of those tools, and I knew exactly what happened. But this is not true anymore. This is now fundamentally different, because by making those compartments of complexity smaller, a lot of the interaction between those compartments of complexity, between those services, have been exposed to the operator, which previously were just hidden behind relatively well-defined interfaces. And if you look at, for example, classical monitoring solutions, they are often designed for a world in which I have my 1 or 5 binaries on the server, and I have maybe 20 servers, and I have a database on every one of those 10 servers, and a web server of every one of those 5, and whatever. This was a very well-defined and very static system. I would maybe introduce a new server every month or every week, unless I'm super large, certainly not every day. Sometimes systems and servers would run for years and years. It was very static and stable. And exposing all of this complexity and allowing everyone to work independently of each other against hard API contracts allows everyone to ship all the time and to deploy new code all the time. And that is why you see observability as such a new term in the industry, because the old style monitoring, even though it is fundamentally the same, the tools which we call monitoring tools are designed for a simpler world where you have a lot less exposed complexity and a lot less moving pieces at the same time. And that is why a lot of the more classical solutions are hitting walls and just cannot cope with what amount of data we have in the overall cloud native and other spaces. There's also something called SRE, Service Site Reliability Engineering, which Google has initially propagated, which is basically just a fancy word for keep the site up. But the thing is, if you have a classical company, you have a lot of fighting between each other. You have the developers, they're paid by shipping the most possible code. You have the operators, they're paid if the stuff doesn't break. You have the product people, they are paid if the roadmap is hit, and you have the research and UX people and such, and they get paid if they do a lot of A/B testing, give new data. So everyone is fighting each other, because everyone has their own priorities, and this creates a lot of strife. But there are different concepts, and to me the core of SRE is this concept. Let's say you go out, you say with 5 friends we are going out for the night, and everyone looks for a few restaurants. If you agree on a budget, you know roughly what you have to do, and everyone can just look at what you can do, and then you just come back together and you won't be completely out of line. Because you have a shared language, you have a shared resource, and this is what aligns you even if you're not talking to each other. Again, a well-defined API and contract, not only on human terms this time. Error budgets are precisely this. Error budgets are the concept of how does the user perceive my system? It doesn't matter if it's breaking because there's so many new features shipped. It doesn't matter if it's breaking because the code is super brittle. It doesn't matter because it's breaking because I don't have enough resources. It is breaking from the perspective of the user, and so I have to fix it here. So if the developers write really bad code and it's breaking all the time, they don't get to ship new features, they don't get paid for the features. The product people don't get paid for hitting the roadmap. So they are going to be unhappy, and they're going to be like, no, we need to fix this, this needs to become more stable. And this is how you can drive a dynamic and how you can actually force people and align incentives amongst people without them even having to talk to each other, because everyone is on the same page. Measuring all of this, SLI, SLO, SLA. SLI is the service level indicator, what I measure. SLO is the service level objective, what I have to hit internally, and the service level agreement, SLA, is where I have to pay someone externally. If you have heard the term KPI, more on the finance and management side, precisely the same concept, but basically mixing all of those three into a melange. So I prefer those terms because they again have layers, and it's more clear what aspect I'm talking about. But if you're talking to a business or finance person, you can just tell them, okay, this cool SLI, SLO, SLA thing from the SRE book, that is just KPIs. And all of a sudden you speak a shared language and you understand each other. You don't have this issue of, oh no, we are not even speaking the same language. Personally, I like to discern between different SLIs, because if the stuff I'm relying on is on fire, my debugging can be quicker. I need to confirm that, yes, this is actually the root cause of my outage. It might be different. But once I have confirmed this, either I can go back to sleep, or I just help the other people fix their stuff. We can also start building a shared understanding. That shared understanding comes in many different forms. I mean, I'm standing here for Grafana, so you can probably guess where this is going. But once I have a system, a similar system where everyone is putting their data, I start using the same language. Again, KPI, SLO, SLA, SLA. If the dashboard is in the extreme just called the KPI SLO dashboard, I'm starting to build shared language. I also pool my knowledge. So this one database person makes a really, really awesome improvement to this and that dashboard or alert or whatever. And all of a sudden, all of the other teams who are also using databases are also having the advantages of all of all of those improvements. They don't have to improve the dashboards and alerts themselves. They just get it for free because someone did it in another part of the org, but as everyone is using the same tooling, everyone gets the same improvement. Same for all the other things. And you really start building a shared understanding of the world around you. Meaning, if you have, like you notice, you go into a meeting and 3 different people start the meeting with a discussion about whose data is least wrong. And everyone is fighting about, no, my data is better, and no, this graph is better, and whatever. If everyone is using the same database, or the same data at least, and using the same visualizations, you don't have this argument anymore because you already went as an institution, as an organization, through a phase where you pooled your knowledge and your everything, your expertise, and you agreed that those are the numbers and those are the graphs and those are the everything which you want to rely on. So you don't have to have this fight every single meeting. And it becomes, again, a lot easier to just have a discussion. You just send over this one email with a report and say, hey, here is a problem. And you don't have to be in a fight about, no, your data is wrong, because everyone who receives this email is agreeing, yes, the data is probably right, and I probably need to fix this. They don't have this cop-out. That's probably all we have time for. That's the last one then, alerting. I have been on call, myself, not anymore thankfully, but I have been on call for 11 years of my life without break or holidays, because I'm an absolute idiot. And I can tell you I would not be married if I didn't have good on-point alerting, because I just, like, it wouldn't have worked, like, wouldn't. Not joking, it's like, I mean, it's kind of funny, but it's also not on some levels. Don't be as stupid as I am, don't do unpaid on-call, and don't put away the pager during holidays. Anyway, the point here is you can burn out super easily. And one of the only ways I was able to not just explode was to aggressively reduce the amount of stuff which sent alerts. And one of those lessons which I learned very early is I can only alert on stuff which is currently or imminently customer facing. If I have 20 database servers, 18 are on fire, and the customer is still buying shoes and they're being happy about being able to buy shoes on my web shop, they don't care. I don't need to wake anyone up. If my SSL TLS certificate is going to run out in 2 weeks and is on a Sunday on 3 a.m., I don't have to wake anyone up. They can do it during business hours. Only wake people up, only scramble them when really the people who consume the service, internal or external, are the ones who are having problems. That's all we have time for. Thank you.
Thank you very much. Any questions? Yes.
Thank you. Thank you. I have a question about, should you be alerted about service being in danger? So it's not down, but it will be down, say, in 2 hours. Should you get an alert? What do you think?
So, depends. If I'm certain it's going to be in 2 hours, I would probably send an alert, because this is imminently customer-facing or user-facing. But there are, like, for example, there are those 99% disk full alerts, which are absolutely horrible. Just make a prediction, easy with Prometheus. Just make a prediction of when will I run out of disk space, and if this is in 3 years, of course I'm growing very slowly, doesn't matter. 2 hours, I would say yes. At least if it's important. If it's not important, whatever. Yeah.
Thank you.
I think there was one more over there.
Yeah, a quick question regarding 2 of the slides. First is the terms that you have used and this alerting. So when it comes to terms and the buzzwords, I have consistently started coming across a new term called as applied observability, which is not just monitoring and alerting, but the tool itself has some capability to take some corrective actions on behalf of the user or the admin. So for example, if the alert says that a particular job or a query is consuming 80% of the CPU, the admin would write a small script and ask the tool itself to kill that query right away, so that the admin doesn't have to wake on 3 a.m. on a Sunday morning. So does Grafana fall under observability or applied observability, or like, just wanted to understand your take on this new term?
I don't think that's very new, to be honest. I mean, the term, whatever, people invent new terms all the time, but like this is the absolute classic cycle of improving anything. Something is not working right. I have to understand why it is not working right, how to fix it. If it happens more often, I need to find a way to fix it reliably. And then we are at the point where you just described, where you want your alerting to automatically take corrective actions. I'm not a big fan of this. I'm a much larger fan, and this is what we do within Grafana. Once I am at the point where, as you say, the operator is able to write a small script, they have enough understanding to actually fix the code and prevent this type of problem from even coming close enough to become a problem. So I relatively strongly believe that it is a mistake to wait so long. You should fix it earlier because you already have all the knowledge. You built the runbooks, you built your understanding of why this alert is happening enough to build a script, then just fix it in the code. There's one caveat, something which like we are also working on and already seeing internal success with is where like common cases with LLMs and such can be done in a way where you have a new, not a known, a new thing, and you have recommendations of, okay, this will probably fix it, and then you can apply this in a tool-driven way. Yes, that's different, but once you have the human understanding, fix it. Don't do applied observability or whatever.
Got it. Thank you.
There's one more here.
Yeah.
Okay.
Any more questions?
I think there's one here.
I just really just like to echo and support what you just said and what your earlier slide pertained to. I always say that architecture protects you against accidental complexity so that you can focus on the actual complexity, which is what you said before. And what you're describing here is you need to understand what problems are structural and fix the structure rather than just putting Band-Aids on top of everything.
No.
Okay.
I have one more question. What do you think about using probability to detect imminent danger?
What do I mean,
Like some distributions, for example.
Yeah,
What is
I get it.
probability of the service goes down like in next 1-2 hours?
So in the abstract, not very useful because in any large data set you will always find correlations. So for example, climate change and the amount of pirates is an inverse relationship over like 200 years. It's relatively robust except for the last like 10 years, but up to that point it was very, very and in any reasonably large data set you will always find correlations. But once you add some understanding, yes, absolutely. 2 examples. One thing which I love doing in Prometheus, you can just look at the double exponential fall-off, which basically both gets rid of cyclic oscillations and also short-term oscillations. And you get a smoother graph of what happened with whatever over time. And then you just define a 10 or 20% boundary around whatever your line is. And then the outliers of this are probably a problem. That's a good example. Another good example would be Explore, which we have in Grafana, where we just do the heavy lifting of all the boring data analysis and just show potentially interesting correlations or outliers or whatever, or drop-offs or time correlations or whatever. And then the human in front of the machine can see, okay, this is good, this is bad, this I have to explore. No, it's not good, I pull out, I go deep here. Basically this combination of a lot of boring computer work and then using subject matter expertise to make the determination of if this is actually the case. If I rely on a fully automated chain, I will have false positives. I will also have false negatives, but that's not in this case. Okay, so have the human, like support the human to understand to the point and then automate it away.
Thank you very much.
Thank you very much.
As soon as the HDMI is working. Next, as soon as the HDMI is working.
Okay, next up, please join me in welcoming Dominic Tornow, who is the founder and CEO of Resonate HQ. Deterministic simulation testing. Please welcome Dominic.
Being here, I'm super excited to be back at FOSSASIA testing. Now we have to live with the yellow slides, but I think we can make do. And curious how my picture is going to turn out. Okay, this is like, it's okay enough. So I am Dominic Tornow. I am the founder and CEO of Resonate. At Resonate, we focus our work on distributed async await, a programming model designed to make scalable and reliable distributed applications dead simple. I am also the author of Think Distributed Systems, which is currently part of Manning Publications' Early Access Program. And the book focuses on dependable mental models to empower you to reason confidently about distributed systems. So it's fair to say that I spend most of my time on distributed systems. Now, distributed systems are known for their complexity. We all just know that distributed systems are complex. We all just know that developing and testing distributed systems is complex. But what, at its core, makes distributed systems so complex? And there are two reasons, two fundamental sources of complexity. The first is non-deterministic partial order, introduced by concurrency. In a concurrent system, we simply don't know what will happen next. And the second is non-deterministic partial failure, introduced by distribution. So in a distributed system, we simply do not know what will fail next. Now, as an aside, feel free to take pictures throughout the entire presentation at any time, but I have marked some slides as an aha moment to highlight what I think is most insightful. So this is one of these aha moments. Now, let's consider a simple, very abstract example to develop an intuition. So let's argue we have two processes, P and Q, each consisting of just 3 actions, 3 steps. So first, let's introduce sequentiality. The defining characteristic of sequentiality is total order and total application. A sequential system executes one step at a time in a predetermined sequence. So there is the sequential composition of P and Q leads to one possible execution. There is simply no room for any alternatives. Next, let's look at concurrency. The defining characteristic of concurrency is non-deterministic partial order. So the concurrent composition of P and Q already leads to 20 distinct possible executions. And finally, let's introduce distribution. The defining characteristic of distribution is non-deterministic partial failure. So the distributed composition of P and Q leads to 69 distinct possible executions. And in a real system, some of these executions are common, while others are super, super rare. So for example, imagine a scenario where a server accepts a connection at the exact moment a configuration reload is triggered. That is a highly unlikely sequence of events. So if we do a simple thought experiment, given that we have 69 distinct traces, let's assume that 10% of these traces are the happy path. They occur 90% of the time. Right? And all of the rest, 90% of the other traces, they are edge cases. Right? They only occur 10% of the time. If we now non-deterministically pick a trace according to this probability distribution 1,000 times, the chances of missing at least one trace is almost 100%. And these rare traces are the ideal breeding ground for the dreaded Heisenbugs. And the term Heisenbug is inspired by the Heisenberg uncertainty principle in quantum mechanics. Right? Heisenbugs are elusive. The rarity of the trace that hides them makes them hard to produce. And by the off chance we actually do produce them, we cannot reproduce them. Right? We'll never go down the same path. Now take a moment to imagine the behavior space of a real-world distributed system with dozens or hundreds of processes, each with dozens or hundreds of steps. The number of possible executions grows combinatorially, and that phenomenon is aptly called behavior space explosion. But concurrency and distribution, they don't just expand the behavior space. Right? They make reasoning about systems almost incomprehensible. Concurrency and distribution introduce daunting uncertainty. And this uncertainty is a true challenge that we face when we design and develop distributed systems. Now, there is a direct correlation between certainty and confidence. When I am certain about my application, I am confident in my application's correctness. Right? Making changes, adding new features and functionalities, deploying to production on a Friday, no problem. So deterministic simulation testing for me is a key component to achieve this level of certainty and confidence by methodically exploring the behavior space, scaling across both space and time. So throughout the rest of the presentation, we will build a foundational understanding of deterministic simulations testing step by step. We will build a dependable mental model so you can decide with confidence if deterministic simulation testing is right for you and your application. So let's begin by grounding our discussion with a mental model of software systems. What is a software system? For our discussion, we will think of a software system as being partitioned into two distinct entities, the environment and the application. The environment represents everything that is not the object that we are developing in testing. And the application represents everything that is the object that we are developing in testing. Our goal is to test the application. And to achieve this, the application under testing conditions must closely resemble the application under production conditions. Right? Any deviation must be non-material. Otherwise, we're just testing something completely different. However, our goal is not to test the environment. The environment is only a means to facilitate the test. Therefore, the environment under test conditions does not have to resemble the environment under production conditions at all. We are free to replace, we are free to mock components as we see fit. So how do we delineate between the environment and the application? What's in and what's out? There is no universal answer. When you delineate, where you delineate depends entirely on your requirements. So here we see an example of a web application composed of three distinct components: a client on the left, a web server in the center, and a database on the right. A reasonable choice is to assign the client to the environment while treating the web server and the database as part of the application. Right? The focus is on testing the web server and database server in composition. However, a reasonable alternative is to assign both the client and the database server to the environment and treat the web server as the application. Right? Now the focus is on testing the web server in isolation. Okay, now that we have a mental model of a software system, when is a software system correct? And how do we establish that a software system is correct? Correctness is not absolute. Correctness is relative to a specification. Consistency models offer a fantastic example of this principle. Take an implementation of a distributed key value store. If the implementation allows stale reads, the implementation is correct if evaluated against the specification of eventual consistency, which allows a read to reflect some previous write. But the same implementation is considered incorrect if evaluated against the stricter specification of linearizability, which requires a read to reflect the most recent write. So the same implementation can be considered correct or incorrect depending entirely on the specification that we choose to apply. As Leslie Lamport explores in his foundational work specifying systems, software systems can be understood in terms of state machines. A state machine is remarkably simple, yet remarkably powerful to reason about software systems. A state machine consists of only 3 components: a set of states, a set of initial states, and a next state relation that determines how we transition from one state to the next state. When we execute a state machine, the state machine generates a trace. A trace is a sequence of states that represent the system's behavior over time. And traces are at the heart how we reason about software systems. Each trace represents a unique execution of the system. Now, a state machine is non-deterministic if the state machine presents a choice, or in more sinister terms, ambiguity. So in this example, from S1, we may transition to either S2 or S3. And this is reflected in the set of possible traces given the initial state of S1. Right? In this example, from the initial state S1, we may generate 2 distinct traces, S1 to S2 or S1 to S3. So given the initial state, we may witness different traces. A state machine is deterministic if the next state relation is a function. That is, if the state machine does not present any choice. In a deterministic state machine, there is simply no ambiguity, just one single predictable path forward. And this is reflected in the set of possible choices given the initial state of S1. In this example, from one initial state S1, we will generate only one trace from S1 to S2 to S3. So given the same initial state, we will always witness the same trace. Now, coming back to the specification and implementation relationship discussed earlier, in effect, a specification is a set of traces. And these traces represent all the valid behaviors that are allowed by the specification. So an implementation is correct with respect to a specification if every possible trace of the implementation is also a possible trace of the specification. And an implementation is incorrect with respect to the specification if some traces of the implementation are not traces of the specification. So, how do we actually establish correctness? There are 2 possibilities: software verification and software testing. In software verification aims to prove that all traces of an implementation are within the specification. and software testing aims to find some traces outside of the specification. Okay, so in summary, if the verification asserts the system is correct, the verification asserts that no correctness violation will ever occur. And if the test asserts that the system is correct, the test merely asserts that no correctness violation has occurred yet. So testing is essentially a search problem, where the goal is to find traces of the implementation that violate the specification, that violate correctness. So how can we increase confidence in a system's correctness? By increasing test coverage. Test coverage has two dimensions, space and time. To scale across space, we extend our test by extending the number of different traces covered by the test. And to scale across time, we extend our test by increasing the length of different traces. However, extending the number of different traces is very difficult. As we saw in the initial example, just randomly stimulating the system will produce more of the same traces, not distinct traces. And additionally, extending the length of distinct traces is also difficult. Many systems have actual timing constraints, such as timeout around crash detection, or timeout around message loss detection, or the time intervals driving rate limiting algorithms. Increasing the length of a trace increases the actual testing time. Now, deterministic simulation testing enables you to scale across space by controlling the scheduling and failure injection, and therefore increasing the number of distinct traces. And additionally, deterministic simulation testing enables you to scale across time by virtualizing time, and therefore increasing the length of distinct traces while shortening the test time. You can, in effect, squeeze 30 years of traffic into 8 hours of testing. And lastly, deterministic simulation testing enables you to reproduce a trace by ensuring that for every starting state, there is only one possible trace through the system. To be methodical and to ensure reproducibility, we construct the system. That is, we construct both the environment and the application so that the behavior of the system only depends on the initial state of the environment and the initial state of the application. The core idea is to substitute the environment with a simulator. Deterministic simulation testing repeatedly executes an application in a simulated environment under changing initial conditions, monitoring that the correctness constraints are maintained across executions. And in practice, this means constructing the system to control otherwise non-deterministic factors such as incoming requests, but also crashes, message losses, and time. So on a high level, we have to think about two interactions: requests from the environment to the application and requests from the application to the environment. The first represents the application input and output, and the second represents the application's side effect, like talking to the network or reading and writing to the file system. And by controlling scheduling and failure injection in the simulated environment, giving a deterministic application, we can deterministically generate an arbitrary amount of distinct traces at an arbitrary length. Now, who is doing simulation testing today? A few companies and projects have adopted deterministic simulation testing. For example, FoundationDB, Tiger Beetle, Polar Signals, Turso, and my company Resonate. And each project took a different approach in designing and developing its application and in designing and developing its simulator. And additionally, there is Antithesis, the first company offering deterministic simulation testing as a service by implementing their own deterministic hypervisor. If you're curious and you would like to dive deeper into deterministic simulation testing, I wrote a blog post a while ago on the fundamentals of deterministic simulation testing. And additionally, I had a recent conversation with Joran, the founder and CEO of Tiger Beetle, a special purpose database for financial transactions, where we talk about writing your own deterministic simulator. Now, deterministic simulation testing requires some investments. However, the payoff is significant. Deterministic simulation testing enables you to methodically test the behavior space of your system by scaling across space and time, making traces reproducible. So you get to squash the bug once you find the bug. And with that, thank you very much for attending my talk, and I hope you have a fantastic conference.
Thank you very much. Are there any questions?
Since the name of it was Heisenberg, it got me thinking about older kind of physics and math. Well, more of a funny question, but Dijkstra, way back when, even before they were even had computers, he wanted algorithms to be provable in the same way that math is provable. Do you think we could ever get there? It seems some of these things are just hardware related, where we just can't say whether the system's so complex we just can't. We don't have that level of theoretical proof. But what would do you think we could get to that stage, or we can use that kind of reasoning?
I am highly biased. I'm a big fan of formal methods. I use, for example, TLA Plus, or recently also PLang and FISB to formally verify the design of the systems, not the implementation. But I believe that deterministic simulation testing gets as close to formally verify an entire implementation as you can practically get. There are, of course, some other methods, like, for example, Daphne, that is a verification-aware programming language that lets you actually write provably correct code, right? But that investment is significant. So again, I'm a huge believer in formally verifying the design of a system, because there you can raise the abstraction level so high that that is actually feasible. And there you have to you have to think about the design envelope. So what failure modes are in, what failure modes are out. But I don't think that anytime soon we will get to actually formally verified implementations. That's where I think deterministic simulation testing can actually practically close the gap.
Thank you. Any more questions?
So that's really cool. I can see how this applies to something like a Tiger Beetle or an end product. Once you start mapping this to meshes of microservices like that trace space just becomes infinite. How do you scale that up beyond an end service?
So the scaling, you're entirely correct, right? The state space explosion also basically means that the state space is infinite and we cannot actually enumerate it, right? But so based from my personal experience at my company, even so that the space state is infinite, you can get actually very, very far. So at this point, our deterministic simulation testing finds bugs where we are basically like, oh my God, why are we even fixing this? This is not going to happen in 500 years of runtime, right? So, and we basically have the idea or the notion that if our tests uncover bugs that far out in the edges and fringes of the system, that basically means we can have a very high confidence that the bugs in the center of the system are already eradicated. So while you're correct, there is basically no way to enumerate all traces. My practical experience points at the huge payoff if you run this thing continuously in your CI for a few hours.
Thank you. Any more?
A question about, have you looked into doing this from the other direction? So instead of running the code and doing traces and stuff like that, have you looked into analyzing how the code looks like and what it can and not do, so you can actually try to prove the code that it's right, because it should be, because yeah, of course you cannot simulate the whole thing, it's a combinatorial explosion, but otherwise if you go from the other side, you should be able to cut a lot of this out of the testing and to actually be able to prove that something is correct.
Yeah, so I have recently started to experiment with Daphne a formal verification aware programming language that when you actually construct the Daphne proof, you can be sure that this is correct. It's mathematically proven. Very, very cool, very, very involved so. So that is, it is really pulling teeth.
Yeah, one question. I've worked on formal specification of languages for quite some time, and one of the typical patterns to model, to give a formal model of the specification is observable state system, which is probably very close to what the testing space does. Do you think it's possible to go back and forth between the two? Because the information you get from deterministic testing could show you parts of a proof that, well, needs to be fixed, or a proof that is incorrect. I mean, we know that not all proofs are correct. Or also go the other way around. If a proof, you try to prove something formally, you should actually get also a trace that on the test side that exhibits the incorrect behavior.
Short answer, yes. So yes, I think that is possible. As far as I know, large companies like, for example, Amazon and AWS are actually employing something like that. I have no personal experience with that, but based on the formal specification of the system, they generate traces, right, out of the formal specification of the system, and then feed that trace after a translation step. Feed that trace into the system and check if that trace is also a valid trace of the system, therefore closing the loop in the other direction. Very, very cool stuff.
Oh, you have to have your own formal specification language in your system then too.
Yeah, basically.
And Dominic will be around, so please, you can catch him in the hallway track outside after this. Thank you very much, Dominic.
Thank you very much.
Next up, we have Ruchi Pakle and Ruchika Surayavanshi, who will be talking about Ansible automation platform for streamlined developments. Please welcome Ruchi and Ruchika.
Okay, so first of all, good morning to everyone. We are glad to be here. And the topic for today's presentation is effective service integration testing with the help of local stack, Ansible, and test containers. So as we all have seen in our day-to-day life as a developer journey, there are multiple services, especially if you are working on CDK applications. So when we are working with cloud, there's a lot of issues while integrating those test cases. So that we'll be presenting today. Yeah, so before we get started, let me just introduce ourselves. I'm Ruchika Suryavanshi. I'm a software engineer at JP Morgan Chase, along with my co-speaker, Ruchi Pakle. She's a software engineer at Red Hat. So let's just go through the agenda first of all. We'll start with what problems we as a developer face in our day-to-day life when we are working with especially the CDK applications. We'll see what is service integration testing, how dependency graph help us to analyze those services. Then we'll see how the local stack can help us to solve this problem, and we'll see how to set up the infrastructure with the help of Ansible, and then testing with the help of test container, followed by a demo where we'll be showing a small application which was deployed with the help of these three applications. And all the questions we can park it at the end of the session. So yes, so the developer challenges that we face in our day-to-day life. What the development cycle goes like, we develop a feature, then we commit it, push it, all the feature changes, everything, then PR approvals and all this thing happens, and then it goes through development. But what if then I realize, okay, I missed this certain test case at this point, but now my changes are already deployed. In this case, I have to do this process again. So I don't have any control on the cloud, what's happening. So the first problem is that I wanted, as a developer, I want that full control, how my services are going to interact with each other, and at what certain point it might get failed. So I want that control. Second is that in this entire cycle, develop, code, push, deploy, and understanding if there's any bug. So understanding that there might be an issue that at this certain stage that we get to know at the later point. So I want that control in the initial half. Secondly, in this point, in the entire flow, there's a lot of delay that happens. Second is that there's a cost. So when we are calling cloud services, it comes with a cost. There's a billing factor. So for testing, I don't have to rely on something that includes costing. And again, there's a huge workflow. And the third problem is, again, it's a very standard problem that we all must have seen, is that it works on my local, but doesn't work on the actual cloud. It might be certain issues like dependencies might be failing, one dependent service might be dependent on some other dependent service, and that dependent service might be failing. Or maybe the version in my local is different, and the version which is there in the cloud, it might be different, it's failing because of that. So these issues we are tackling in our day-to-day life that we could solve with the help of this thing, and how we can test it. So the next is service integration testing. So as we can see, when we have a large-scale application, there are multiple services that are involved. So these services interact with each other. So when there is a lot of large-scale services are interacting with each other, there is a huge dependency issue can be done. So we have to test each service when one service is interacting with the other and how they will be performing. So when all the components will be interacting with each other, I want to make sure what would be the next expected output. So that should be matched. I want this entire thing in my local. So that could help us in the integration testing, and this could help us to not take those bugs in the production level. We could solve it in the CI integration part. Next comes is understanding the dependency graph. As I have mentioned, understanding the dependency, it's itself a huge task, since there are a lot of services that are interacting with each other. So it's always best to draw a dependency graph which will help us to visualize how the dependencies are interacting with each other, resources are collaborating with each other, and what exactly the mind map looks like. This will also help us to understand both the internal and external dependencies that happen. Next is that we could, at the initial phase, while we are creating certain integration testing, we are able to understand the entire flow, that how services are going to interact, so that we can write more effective service integration testing. So here it comes local stack. So local stack is a simulator which will take your entire AWS services in your local. You don't have to pay anything. It will be a simulation of all the services, be it S3, be it any databases you are using. It will simulate that on your local directly. It is not going to affect your cost at any, because it is not actually calling the AWS. So you can run the AWS application or Lambda entirely in your local machine without any remote connection to your cloud services. Third is that it's ideal for testing complex CDK application, especially when we are working with the cloud applications. Then it says that test AWS without any AWS connection. So you can have the entire local setup, AWS setup in your local. So let's just understand how the local stack architecture works. So first of all, we need to give a configuration, like what all services that I need to have in my entire application. It could be S3, some resources, what DB I want. I can give all of that in the configuration that will be stored in your environment variable. Then there's a persistent state. So whenever the local stack restart, it might refresh your state of maybe S3 or any database which you have, DynamoDB and anything. So that might cause some issues while testing it. So we can store that data in a state which is called as a directory, data_dir, where you can store these states of your services. Second comes here in this CI part, it comes your local stack. This local stack acts like your calling the actual AWS. So whenever the calls happen, API calls goes to the local stack and it will work as a AWS service. So if you are creating an application which takes the data, it stores the those files into S3. So what it will do, it will take those files, it will store in the local setup. So it will work similarly what the AWS services are working. Then we have Lambda functions and Docker. Docker is something for Lambda functions, we need to create certain virtual environment that will be closed for certain Lambda functions, and it will also get stopped or destroyed once the work is done. So this is how the architecture works. Moving on, supported AWS services. So local stack emulates over 90 Amazon Web Services as of now, and these are the core services that we all have. Then these are the multiple options which you can install the local stack in your machine. One is the Docker container, second is Docker Compose, and third is the GUI based Docker desktop application. It supports all three Mac, Windows, and Linux. Then we can include the CI/CD workflow in our local stack. So whenever the developer pushes the code, it goes to the version control. After that, it goes to the CI runner. You can use any of your CI runner. Then there is a cloud pods for storing the state, your application, whatever the states that you are giving. Then there is a infrastructure where you can store how the infrastructure will be working. And the actual local stack sits over here. After testing all this part in the CI, it gives you a test report. In this part, majority of your test and the entire application is tested so that you won't feel any bugs in the deployment part. You can easily go to the CD pipeline part. So moving on, Ruchi will take over with what is Ansible. Thank you. Over to you, Ruchi.
Thank you, Ruchika. So now let's talk about what's Ansible. Ansible is an agentless automation tool that signifies configuration management, application deployment, and infrastructure orchestration. It uses like YAML-based files to write the playbooks and making it easy to automate your repetitive tasks, right? So one of Ansible's key strength is idempotency, meaning that you don't have to run it again and again, and when you will run it, it won't make the changes unless and until it's required, making it like consistency and prevents the unnecessary modifications. Another advantage is simplicity. Ansible does not require agents running on remote machines. You can just run it using SSH or APIs, and making the setup and maintenance very straightforward. And now when combined with local stack, Ansible can provision AWS resources, allowing you to test infrastructure changes in a safe and controlled environment before deploying to real AWS. So this makes it a powerful tool for DevOps workflows, CI/CD pipelines, and cloud infrastructure automation. Now that we know what Ansible is, let's dive into how it works. So Ansible follows like a declarative approach where if you define your desired state of your system, and Ansible ensures they match that state, right? So let's break it down. So we have the Ansible management node where the management node is the node where Ansible is installed, and then we have our inventory file where you provide, you define your target systems, and it could be anything, right? It could be your Linux machine, Windows machine, it could be cloud services like AWS, GCP, Azure, or network devices for, in that case, like Cisco, Juniper, or Arista, right? So it's like a host.ini file where you define your host and variables to connect to the system. And then the next we have is modules and playbooks. So they are the building blocks, right? So like they handle the specific scripts, and you provide specific modules, roles and variables in the YAML file, which is the Ansible playbook. And using that, you can like create your devices. You can create like a playbook is a YAML file that contains one or more plays defining what should be done on each system. So, yep. Yeah, so the playbook syntax and structure, so we have different plays and each plays have different tasks, and you can just run them using the Ansible playbook run command. Next slide, Ruchika. Yeah, so writing an Ansible playbook. So the example playbook could be, you can provide the name of the playbook, then we have the host, where you provide your host, like web servers or any target system that you want to define there. And if you want to run it as a root user, you can just give it like a become user equal to root and become variable as yes in that case. And you can define specific tasks. So first task could be like ensure Apache is at the latest version, and you are like just installing the HTTPD package. And next would be ensure Apache is running, and service could be like, yeah, HTTPD and state is started. So, yeah, so integrating Ansible within local stack. So we use Ansible playbooks to automate the setup and configuration of local stack. So Ansible uses like provision AWS like resources, and it uses Ansible tasks to create the resources, S3 buckets, DynamoDB tables, and you can just preseed the data into this like Ansible playbook, create files, and yep, so you can just like create a local stack container using the Ansible by defining specific task here. Then we have testing using test containers. So test containers is basically an open source library for like bootstrapping real dependencies. So we have lots of dependencies in our code, right? It could be like databases, message brokers, orchestrators, web browsers, like there could be multiple dependencies. So test containers provides an easy way, like lightweight APIs to connect to those and tear them down step by step. So they just run, like using the test containers, it just runs your integration test. It just runs them on the container. It and yep, it also destroys them after the this thing. So yep. Yeah, so next slide is like what problems do test containers actually solve, right? So we have like a cloud native infrastructure and microservices in our code base. So example, I have my service running and it's connected to a data store, and then we have like API gateways which is connected to different services in this case, and we have our message broker Kafka, which like produces, yeah, the producers receive the data and it consumes it consumes it from a different service, and then it pushes to the cloud. So like, you know, every test, like everything related to testing is done inside the my service application, and a full-fledged test comes out of it. So yeah, so what I own, test and deploy, you can just have full control over those, and it doesn't break your CI as well. So that's a great thing, right? Yeah. So test containers, Ansible plus local stack provides an automated AWS testing, and how it works is like Ansible orchestration. It provides an infrastructure platform which runs playbooks to spin up and configure the local stack with the required AWS services, and it executes them, like automatically launches a fresh local stack container for each test run, providing it a very realistic approach to manage your databases. And yeah, I guess we don't have the time for demo, but yep, so we can skip it. Yeah. Okay, thank you. Thank you so much.
Unfortunately, so much content, so little time.
Yeah.
But certainly there's a hallway track for everything else. So after this, you'll be around, right?
Yeah.
You can catch them. So again, thank you very much.
Yeah.
Next up, We have, before that, sorry, do we have, is Dimitri in the room yet? Could you please make sure your slides are loaded? Thank you. Okay. Next up, we have Veer Kumar Patil, who will be giving a talk titled Beyond the Layers, Testing Microservices and Nanoservices Effectively. Veer Kumar is the Principal Software Quality Engineer at Red Hat. Please give a round of applause to Veer Kumar.
I just wanted to check whether the slides are working. Okay. So good afternoon, everyone. It's great to be here today at FOSSASIA 2025. This is my first international conference, so a bit nervous, but still I'll try to deliver my best, okay? So today I'm here to speak about something that's transformed the way we build, test microservices and nanoservices. As software systems evolve, monolithics are become broken down into smaller, more modular and manageable components. While this flexibility increased the scalability, it also introduces some challenges, especially when it comes to testing. And that's exactly what we are going to see and we are going to explore in the today's talk, Beyond the Layers, Testing Microservices and Nanoservices Effectively. So before actually jumping onto the topic, let me quickly introduce myself. So my name is Veer Kumar Patil, Principal Software Quality Engineer at Red Hat, an open source contributor who believes that you have to give to community to grow in your career. I'm also a mentor in different testing communities, actively involved with Test Tribe, which is a Pune-based testing community where I contribute more. I'm also a YouTube content creator, sharing insights and some tutorials around testing. Apart from that, with Red Hat, I got an opportunity to review a book on the Cypress, which got published in 2023 around ultimate web automation testing with Cypress. And I proudly test websites, so I'm a proud tester. Why I say that? Because I feel quality is a prime importance when you wanted to build a product. Okay, and I know I just found bugs whatever I touch, I found bugs. That's why I called. Even today, before coming onto the stage, there was an issue with my talks, times. So previous talk was of 25 minutes and mine was 15 minutes. And the previous talk was starting around 11:45 and this was at 12. So it was a kind of small bug onto the application that got caught thanks to one of my friend who called me yesterday. So that's why I called it a proud tester. So without further ado, let's get started. So my talk is mostly around some questions and those questions we'll try to answer over the period of time. So, okay, so first question is, how do monolith microservices and nanoservices differ in architecture and scalability? So let's try to understand this particular thing first. Okay, so in order to explain this, right, the technology has been evolved over 2 decades, where a single monolith architecture will consist of a tightly coupled system where UI, business, data access layer has been, kind of unified into a single code base, which are tightly coupled. It has a simplicity. It has a simplicity. It can be simple deployment, but it also had some cons. Like these particular architecture is difficult to scale. Okay, when it comes to deployment, these applications are pretty slow in deployment. And imagine there is a bug in the system and that can take your entire application down. Okay, so these are the cons, that has, taken over with advancements in the technology where the microservices architecture comes into picture. So when it comes to microservices, right, so how it differs from the traditional monolith architecture. So basically, you break down the entire application into small independent services, and each service is responsible for a specific business function, which are easy to scale, independent deployment, and you can isolate it from one another, still able to interact with one another. So with this, even though it provides advantages, it comes with some complexities as well. The complexities around infrastructure, high inter-service communication, because in order to interact with your entire application, you have to be, interact with different services. For example, you can see on the left, microservice is interacting with another microservice, and another microservice is actually interacting with your database. With that, let's jump onto the nano service part itself. So nano service is, I'll give you an example, real world example, how nano services differ from the microservices, okay? So imagine a website where you can see the green box over there, and inside that you see orange boxes, different orange boxes. Those orange boxes are talking with different nano services to get that particular data. For example, you're generating headline over there, or you might wanted to have some data from your weather information, or you wanted to update a match score. Like for example, there are football matches, or there are some cricket matches going on. That particular data can come from a nano service and will be available on the page. Another example that Red Hat is actively using is on their home page. So these components are built with the data coming from the nano services. So next question is, why is testing microservices and nano services different from the monolith application? So I'll quickly change the slides, okay? So monolith applications are tested as a whole, while the microservices and nano services are independent, distributed, and loosely coupled. Challenges arises due to dependencies, and challenges arises due to inconsistencies across the data. Now let's go on how you can better test these things. What are the different test strategies that you can apply for testing microservices? Okay, so I'll quickly jump onto the slide. So these are the traditional testing strategies that you can apply for any of the microservices, like unit testing, integration testing, contract testing, E2E testing, load testing, and resilience testing. We'll jump on each of the things once I explain the stuff, okay? So how you test API interaction between microservices, okay? So for example, you have a microservice application for an e-commerce website where you have a user service, you have a login service, you have a payment service, and you have a actual booking service. So in order to test this particular interaction, you can always look for the unit testing where there are price calculation involved. You have an interaction between the booking service and the payment service. You can test out that particular integration with the integration testing. You might have an end-to-end test flow with your web UI, a web application, or a mobile application. So for that, you can use different tools as well. For unit testing, you may use JUnit if you're using Java-based, microservices design. If you are using for example, if you're using a JavaScript-based tests, then you can use Jest for writing your unit test cases. When it comes to front-end stuffs, right, you can always rely on the end-to-end test for the tools like Cypress, Playwright, which allow you to do that testing, front-end end-to-end testing. Then how we can perform load and performance testing on microservices, okay? So this is one of the critical aspect of a testing where you wanted to test out your app is performing very well, or your microservice is performing very well under stress. So for that, you can use tools like Gatling, which allows you to, which allows basically you to do a performance testing. There is a tool called as Locust, and apart from that, you can use a tool called as JMeter, which allows you to perform the load testing. How do we implement chaos engineering for your microservices? So basically, this is kind of resilience testing where you wanted to ensure that your application behaves properly in case of major failures. It should handle those kinds of failure in graceful manner. For example, your payment service is not available. Then in that case, how your front end should react when these kinds of situation happens. So you have to test those things when it comes to resilience testing or performing the chaos engineering around your services. What are the best practices for security testing in microservices? Okay, so with the advent of technology, the security testing is also a important aspect when it comes to microservices. You have to rely on ensuring authorization and authentication of your services has been implemented properly. You're not over sending the data or over exploiting your data whenever the response is sent to the front end applications. Lastly, how does CI/CD help in testing microservices and nanoservices? So everybody is talking about continuous integration and continuous testing, where you have to make sure that testing in CI is been primary focus when it comes to QA. They have to make sure that whenever a push has been made or MR has been created for a service, it has go through the testing steps, and that should be of a prime importance. A key takeaway is like if you wanted to build a quality service, right, you have to combine your integration testing, contract testing, performance testing, continuously monitor your service performance, use mocking and CI/CD pipeline enhancements. I'll not take 2 minutes. A small bug, so these are the key takeaways for a QA. A small bug in one service can break everything, so test wisely. If you are a developer, clear code, clear test makes strong system. So make sure that you write a clear code and unit test cases. And if you are a business leader, please make sure that quality isn't an act, it's a habit. Well-tested microservices mean fewer surprises. So make sure that whenever you are delivering a product, give some time to testers to test the applications. With that, I am close to my slides. So this is one of the collection where you can find the different resources available for testing. So Postman has very good collection around how you can perform integration testing, contract testing, async operations, and all those. Lastly, I just wanted to share my coordinates where you can connect with me, my GitHub, LinkedIn, YouTube, and thank you everyone for listening me.
Thank you very much. I'm afraid we don't have time for questioning, but the parting remarks were indeed some very wise words to keep in mind. So next up, we have Dmitry Shurupov, who is the co-founder and CNCF ambassador of Balak GmbH. He will be giving a talk titled WRF and its ecosystem, efficient software delivery in Kubernetes and beyond. Please welcome Dmitry.
Hi everyone, my name is Dmitry Shurupov, as it was said already, and I'm from German company called Pelarg. But I will tell about open source project which existed before this company was formed, and I was involved in it from very beginning. The project is called WRF. WRF is a Dutch word for shipyard, so you can see a shipyard as the logotype of this project. I will tell a story of one DevOps agency, but actually DevOps is quite a controversial word today, so I would say that it's outsourcing company that was rendering IT operations, CI/CD implementation, and this kind of stuff for other businesses. The wizards from this company were always trying to implement software delivery for different companies. These companies were of different size, different industries, they use different technology stack and so on. And they tried to implement software delivery because of all of this on case-by-case approach. Later, in 2013, Docker entered the room. And of course, it was not really a revolution technologically because containers we knew before, and even these wizards already played around LXCs and other solutions before Docker. But what Docker really changed, it was the simplicity of how you can handle containers. And so these wizards started to invent some magic wands using their favorite language. You can guess what was that. In addition, of course, to the magic words language, it was Bash. So they started to write some reps around the Docker, and line by line, script by script, it became bigger and bigger. After they realized that it's huge enough, they rewrote it to Ruby, because Ruby was the language of Chef. This infrastructure as code tool was very famous for requiring you to write Ruby recipes to describe your infrastructure. Then Golang came to the world and became really popular, and so they rewrote it to Golang, so that's why you can see this nice gopher here. And of course, because this company was mostly operating with open source software, because IT operations were all about managing your web server, your Linux, your databases, whatever technologies were open source, they also decided to make this tool open source. And not only because of this, but because more people can collaborate on it, and it will be more benefits for bigger community. At the same time, even a little bit before, another magic was happening in the world, and here you can see Brandon Burns and Craig McLuckie, who during Google I/O 2014 conference introduced Kubernetes. I will not delve too much into the further history. I will just say that after they introduced it, it was something industry wanted so much, so we started to adopt it widely and even sometimes wildly, and it became the industry de facto standard. And it also brought the bigger cloud-native world to flourish, because it's not only about Kubernetes, but it's also about monitoring. So then Prometheus came into place, about container registry, then Harbor appeared, and so on and so forth. And also because the market was quite competitive, the companies who needed software delivery based on Kubernetes, they also wanted more and more. First of all, the faster time to market. So the whole universe was born, the universe of cloud native, spearheaded by the CNCF organization. And let's go back to the project Verve. Today is a CNCF sandbox project, but it has been developed for over 9 years already. And to say in general, we can describe it as a command line tool which you can use to build, deploy, and distribute applications in Kubernetes. I also like to call it a glue, because it glues many existing well-known technologies, such as Git, Docker, Helm, Builder, and of course Kubernetes. But it not only glues them, but it also offers more features on top of them. This overview, how basically Verve operates, you need to describe your application in a Docker file, which is de facto standard again, in Git. Then Verve, what will do, it will build your container images and push them into container registry. Then you also need to define your Kubernetes resources for this application, for these container images in Kubernetes, in the form of Helm charts, which will be also placed in your Git. And then Verve will deploy everything, these resources and these container images, to Kubernetes. So basically we can say that what Verve does, it syncs your Git descriptions, your desired state, with actually running application in Kubernetes. Here you can see an example of a small project which has been already containerized. It has backend and front end. And to use Verve, you just need to add a simple YAML file which will actually refer to your existing Docker files. Then you can benefit already from extra features, we will talk about them later, that Verve offers, for example, in Helm charts. Then you need just to execute one command, Verve converge, and you will see this application running in your Kubernetes. Now, what about the advanced features Verve offers on top of existing solutions? First of all, it's the determinism principle. We like to say about this that what you get is what you get. So the idea is that everything is reproducible and reliable, because what you defined in your Git will always be in your actually running application in the Kubernetes. In terms of build, Verve integrates with two backends. It can be like classic Docker and more fancy Builder, because Builder allows you to do rootless builds. It allows you to do in-cluster builds, in Kubernetes clusters, how we usually build our container images in the cloud-native world today. But on top of them, it offers incremental builds, which means you will never build again the parts which you don't need anymore. And also it offers content-based tagging. Also it offers parallel building and many other features. For deployment, it uses other tool, Nel. This is a side project, but originally Verve used Helm to deploy the applications, but because it needed more features and Helm development was not active during last few years, we actually forked Helm and called it Nelm and offered more features on top of it. Now it's a separate project which can be used anywhere you like. That offers more features, but we don't have much time to tell about them. You can read from the slides, and there's some illustration how they work. Another part of advanced features Helm offers are related to resource tracking, and for this we have also separate project, which is called KubeDoc. KubeDoc is Go library, which you can also use in your project separately from everything. And basically it allows you to see such nice interactive view of how your deployment process is going on. You can see which of your resources were deployed or not, what happened with them, which operations failed, and so on. This is the feature which original Helm lacks very much. So let's go back to Verve. In terms of application distribution, Verve offers bundles. It's a way to distribute your images and all related artifacts as a single entry. And what's nice, you can then deploy them not only with Verve, but any software you use. It can be original Helm, Argo CD, Flux, or any other tool you prefer to use. The latest big feature is Smart Cleanup, which means that Verve will never remove anything you need in your container registry, but it will remove everything else, so it will not become too huge. And also important that Verve is not only about its features, but also about its community. And now we have two actively contributing companies, a lot of GitHub stars, numerous agencies, other agencies that rely on Verve. And we are aware of at least 15,000 projects, it's like Git repos, which are using Verve today. There are some other side projects that emerged during the development of Verve, such as this one. This name is very funny, it's TRDL, and you should never confuse it with TLDR, but we made it specifically. It stands for True Delivery, and basically the idea is that it's plug-and-play solution for your users if you want to deliver them something from your Git repo. So user one time installs your software through TRDL, and then whenever he or she runs this software, will always get the latest version from a relevant release channel. It can be stable, alpha, beta, whatever the user itself chooses. We will skip this. Another side project is Kubernetes guides, because we realize that Verve is not only used by operators, but also by developers. And not all the developers are well aware about how Kubernetes works and how you should deploy everything there and so on. So this is a very nice documentation project which covers 3 different languages, frameworks, and it should be very helpful for developers who want to learn about Kubernetes, because despite its strong practical focus, it also explain some basic things, and developers will learn how they can deploy first very simple application and then more advanced, more real-world application, which is implemented on their preferred framework with databases, files, login, and so on. So to sum it up, WRF is about automated best practices for software delivery, which are implemented in opinionated way and based on well-known existing technologies. And what's important, it's more than just a CLI tool. As you can see here, this is a project, and I want to highlight is that while you develop a big open source project for a continuous time, then more smaller projects can emerge, which will be used separately by the community, and everyone will benefit. So they don't need everyone to use WRF, but they can benefit from this library or from this other tool, and they can contribute back to this, and all the bigger community will benefit from it. So that's it. There are some links where you can find the information I was telling you about. And here's my last slide. I can also advertise a little bit my Telegram channel, Kubernetes, if you're interested in more CNCF projects, Kubernetes-related news and everything. Subscribe and enjoy. Thank you.
Thank you very much. Are there any questions? No. Well, that's very interesting. I mean, I still remember the days when we were pushing code up to production FTP. Yes. Right. We have come.
We all remember it.
Yes.
With tears in our eyes.
Except some of the young ones who don't know what FTP is. Okay. Well, if there are no more questions, first of all, I want to everyone to join me in acknowledge and thank you our support, AV support, and our speaker support, without whom this would not be possible. Thank you. And so now we are officially breaking for lunch, and this track will continue in 1 hour at 1:30. Thank you very much.